Chapter 15. This chapter is titled Acid-Base Equilibria. Our outline is common ion effect, buffers, titrations, where we will consider strong acid, strong base titrations, weak acid, strong base titrations. We will do a calculation of Ka and do a strong acid, weak base titration. The first area is common ion effect. Back in chapter 14, we looked at reactions where we took an acid, we put it in water, we looked at the products, A- plus H3O plus. We worked with bases where we put them in water and we found we have Hb plus OH minus. We calculated concentrations of products. We calculated pHs, percent ionizations, and so forth. But we always only had a single solute, such as HA or B. We did calculations in that chapter also with salt solutions. Now we will look at how the pH of a weak acid or base is affected by the addition of a related salt. The effect of the salt, the ion in the salt, on the pH is called the common ion effect. Okay, so let's take an acid, a weak acid, HA, put that in water. It's in equilibrium with A- plus H3O plus. The system is at equilibrium, let's say. Then we add NaA, where NaA is a salt. It's a related salt because the anion A- is the same anion that's part of our acid reaction. It's the conjugate base of HA. The effect of the basic A-, it will shift the equilibrium to the left. Think of Le Chatelier's principle. We add some A-, it moves the reaction back toward reactants, and it will make the solution more basic and increase the pH. We'll consider HNO2, that weak acid, and how its pH is raised by the addition of basic KNO2, so potassium nitrite. We calculate the pH of the solution containing the common ion in the same manner as before. And as usual, spectator ions have no effect on the equilibrium. The spectator ion here would be the potassium ion. Alrighty, so here's our problem. Consider the weak acid HNO2. Ka for it is 4.0 times 10 to the minus 4. We will first calculate the pH of that solution without the common ion. So calculate the pH of 0.50 molar HNO2. So we set up our ice table, put in our initial concentrations, represent the change by X and negative X, get the equilibrium ones, and write out the equilibrium expression. Ka equals A- times H3O plus divided by HA. We have 4.0 times 10 to the minus 4 equals X squared over 0.5. X is 0.014. We do the check, it's less than 5%. So we're okay. Since X is the H3O plus ion concentration at equilibrium, that we have H3O plus concentration is 0.014 molar. We calculate the pH from the negative log of the H3O plus ion concentration, and we get the pH is 1.85. Now we calculate the pH of a solution that is 0.50 molar HNO2 and 0.10 molar KNO2. So we have some of the common ion NO2 present, NO2 minus. Alrighty, we fill in the ice table in the same manner, except that instead of having no NO2 minus initial there, we have some. So we have 0.10 as the initial amount of the NO2 minus. Otherwise, the table looks more or less as it did before. We make the approximation. We can drop x with respect to the 0.5 and the 0.10. Alrighty, so we have x coming out to be 0.0020. We do our check. We check our x with respect to each one of those we dropped it with respect to. The 0.50 and the 0.10, they're both less than 5%. So we have the H3O plus ion concentration equals to 0.0020 molar. We take the negative log of that and we get the pH is 2.70. So indeed, the pH went up a little bit as we added basic KNO2 to our solution. Buffers, that's our next section as a subsection of the common ion effect. An important application of acid-base solution containing a common ion is for buffering. A buffered solution is one that resists changes in pH when either acid or base is added to it. So buffers are very handy in a chemistry lab. We often have to store items like pH probes in a buffer. They need to be held at a very constant pH. So we have buffer solutions which resist changes in their pH by some kind of acid or some kind of base getting into them. They can resist changes in their pH because a buffer contains either a weak acid to neutralize any added base and its conjugate base to neutralize any added acid, or they might be a weak base to neutralize any added acid and its conjugate acid to neutralize any added base. And it contains approximately equal amounts of HA and A minus, or if it's the basic kind of buffer, B and HB plus. Consider the acetic acid and acetate ion buffer. So that means a buffer made of HA and A minus, where HA is acetic acid, C2H3O2, and A minus is acetate ion, which is C2H3O2 minus. So we see the equilibrium, HC2H3O2 plus H2O in equilibrium with C2H3O2 minus plus H3O plus. So we have amounts of the acetic acid and the acetate ion that were there in the beginning, and we have an equilibrium established where a little bit of the H3O plus forms, but very little. When trace amounts of acid are added, the added acid, like HCl, but the important part of it is H3O plus, it would react with C2H3O2 minus to form HC2H3O2, thereby leaving the pH nearly unchanged. So we have our acetic acid acetate ion buffer. That's our first reaction we're seeing there. But a little bit of acid is added to it. So what that little bit of acid is going to react with is the weak base part of our buffer, the C2H3O2 minus, and it will follow that reaction. Notice that that reaction, the second reaction shown here, has a yield sign. Whenever we have an acid or a base in something other than water, the reaction, that is to say, whenever we have an acid or a base with a base or an acid, that reaction goes all the way. So when we don't have water involved as one of the reactants, typically the reaction goes all the way. Alrighty, so that's what would happen if acid were added to our buffer. When trace amounts of base are added, the added base, OH minus, reacts with C2H3O2 to form C2H3O2 minus, again thereby leaving the pH nearly unchanged. So take our first reaction. When a little bit of added base is added to it, what it's going to react with is the weak acid, the acetic acid. According to this reaction here, the third one, we have the weak acid HC2H3O2 plus O2 minus yielding C2H3O2 minus and water. That reaction again goes all the way because we don't have water as one of the reactants. So in other words, the weak acid acts as a source of protons for OH minus, and the weak base acts as a proton acceptor. So of our original buffer, the top reaction, the acid part of it will react with any added OH minus. The base part of it will react with any added H3O plus. Blood is buffered in the range of 7.35 to 7.45. If we're not right around what our blood needs to be at pH-wise, which I think is around 7.4, then we are very sick. Our body protects itself by having buffering systems within our blood that help to keep our blood in a very small pH range. Our blood is buffered with several systems, among which the carbonic acid and hydrogen carbonate system is the most important. And that's the buffer we see here, the top reaction, H2CO3 plus H2O in equilibrium with HCO3 minus plus H3O plus, where the acid part of it is the H2CO3, the base part of it is the HCO3 minus. The HCO3 reacts with any added bases, such as urea, that is formed during the catabolism of proteins, and the HCO3 minus reacts with any added acids, such as lactic acid or ketone bodies. The reaction with added base, so that would involve the acid part of our buffer, the H2CO3 plus that added OH minus, it yields HCO3 minus plus H2O. The reaction with any added acid that would occur, well, that would be the base part of our buffer, HCO3 minus plus H3O plus, forming H2CO3 plus H2O. So there, in that sense, our body can withstand small changes in added acid or added base. So blood is well buffered. The addition of 0.01 moles of HCl to 1 liter of blood lowers its pH only from 7.4 to 7.2. That's a change in pH of only 0.2. So obviously we would never do this to a human, but rather imagine a liter of blood in a laboratory. We could add HCl to it. Prior to adding the HCl, let's say we measure the pH and it's 7.4. Then we add the 0.01 moles of HCl, which is the source of H3O+, and we would remeasure the pH and find it to be 7.2. So that's a pH change, delta pH, of only 0.2. Too much for the human body, but still not much on the grand scheme, because in this next problem, we will calculate the pH change when 0.01 moles of HCl is added to 1 liter of water, and we'll see a much bigger change. So think about it. What is the initial pH of pure water? Hopefully you realize it would be 7.0. When we add the 0.01 moles of HCl to 1 liter of it, we have the H3O+ ion concentration to be 0.01 molar. So the pH, the final pH, is the negative log of 0.01 or 2. So we get that the delta pH is 7 minus 2 or 5, a much bigger change. And in this way, we're showing how blood is well buffered. Okay, so now we'll do a problem, a chem lab type problem. A buffered solution contains 0.25 molar HA and 0.56 molar NaA. Ka is 1.8 times 10 to the minus 5. Calculate the pH of this initial solution, of this solution. So we run through the usual way. We set up our ice table. We put those initial amounts, 0.25, 0.56. We have the equilibrium amounts. We put them into our equilibrium expression. And we have 1.8 times 10 to the minus 5 equals 0.56 times x divided by 0.25. We get x to be 8.04 times 10 to the minus 6. X represents the H3O+ ion concentration at equilibrium. So we have H3O+ concentration is 8.04 times 10 to the minus 6 molar. We take the negative log of that and we get 5.09. Now we're introduced to the Henderson-Hasselbalch equation. An easier way to calculate the pH of a buffer is to use the Henderson-Hasselbalch equation. Kind of a big name for an equation that's very simple to use. It's okay to use as long as we can drop x with respect to the initial concentrations, and as long as we have a buffer, we have amounts of both HA and A minus. Okay, so going back to our usual equilibrium expression, which I'm showing here at the top of the screen, Ka equals A minus times H3O+ over HA. So that's where we're starting with in deriving this Henderson-Hasselbalch equation. So we start with that equation. We take the log of both sides, and then we multiply through by a -1. So at this point we have negative log of H3O+ equals negative log of Ka plus the log of A minus over HA. And we recognize that the negative log of H3O+ is pH. Negative log of Ka is pKa. So we have pH equals pKa plus log of A minus over HA. That is the Henderson-Hasselbalch equation. Okay, so now we're going to use it. So going back to that problem we just did, if we look at just the initial line, the I line of our ice table, We have initially 0.25 molar HA and 0.56 molar A minus, no H3O plus to start with. So what we have to determine in order to use the Henderson-Hasselbalch equation is what pKa equals. Well, we were told for this buffer, this acid HA, Ka is 1.8 times 10 to the minus 5. So pKa is negative log of Ka, negative log of 1.8 times 10 to the minus 5. So we get pKa to be 4.74. So we have Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus over HA. We have pH equals 4.74 plus the log of 0.56 over 0.25. We get the pH is 5.09, just as we had before, but this way is probably a little bit quicker because it's a buffer, so we have amounts of A minus and HA, and we're simply after the pH, so it allows us to really focus in on that. Okay, next we will calculate the pH of that buffer, that same buffer. We're on part B of that same problem. Calculate the pH after the addition of 0.02 moles of HCl to 1 liter of the initial buffer solution. So the HCl, that's the source of H3O plus, and it's of course an acid, so it will react with the base part of our buffer. It will react with the A minus part. So for this calculation, you might say we have like two parts to it. We have the first part, which involves the reaction that goes all the way to completion, A minus plus H3O plus, yielding HA plus H2O. So we put in our initial amount of A minus. That's what the problem started with, 0.56. We now have 0.02 molar H3O plus, so we put that in our I line, and we have in our original buffer, our initial buffer, 0.25 molar HA. Now, that's a reaction that goes all the way, so we think of the change as not being X, but rather being whichever is the smaller of the two reactants, and that is the 0.02. So that represents the change. It is negative for the two reactants that are getting used and positive for the one that's forming the product. So we have, when that reaction is complete, 0.54 molar A minus and 0 molar H3O plus and 0.27 molar HA. Now is when we go to the equilibrium calculation and we use Henderson-Hasselbalch equation. So we need only write down the initial line of our ICE table. So we write HA plus H2O in equilibrium with A minus plus H3O plus. We put those values, 0.27 and 0.54. Write out the Henderson-Hasselbalch equation. We put the pKa in of 4.74. A minus is 0.54, HA 0.27, and we get the pH is 5.04. It has gone down a little. We expect that because we have added acid. Next is a problem, part C of this same buffer problem. Calculate the pH after the addition of 0.02 moles of NaOH to 1.0 liters of the initial solution. Well, NaOH is a source of OH minus, so the OH minus, being a base, is going to react with the acid part of our buffer, HA. So our stoichiometry calculation involves the reaction HA plus OH minus yielding A minus plus H2O. Now we're back to our original initial buffer. So we have in our stoichiometry calculation and the ICE table, we have the original amount, the 0.25 molar HA, and the initial amount of A minus 0.56. For the OH minus, we have 0.02. Okay, the 0.02 is the change, negative for the reactants, positive for the product. So we have, when that reaction is completed, 0.23 molar HA, 0.58 molar A minus. Now we go to the equilibrium calculation where we put those initial, or those amounts following that reaction. We write out the equilibrium reaction as before, HA plus H2O in equilibrium with A minus plus H3O plus. Notice that no matter what the stoichiometry calculation reaction is, we go back to the way we're used to seeing that buffer reaction. Okay, so we put in the amounts, 0.23 molar, 0.58 molar. Now we go to the Henderson-Hasselbalch equation. We put in the pKa, 4.74. A minus is 0.58 molar. And HA is 0.23 molar. And we calculate the pH to be 5.14. It has gone up now in comparison to where it began because we have added base this time. Our next problem is to work with, again, a buffered solution, and this time it contains 0.58 molar NaH2PO4 and 0.80 molar Na2HPO4. Now, H2PO4 minus and HPO4 2 minus, those are parts, you might say, of phosphoric acid, H3PO4. So what we have here is the 3-step acid dissociation reactions of phosphoric acid. The first one, H3PO4 plus H2O in equilibrium with H2PO4 minus plus H3O plus. That involves H3PO4 and H2PO4 minus. Those are not, one is part of our buffer, but not the other one. So we go to the second step, and that is H2PO4 minus plus H2O in equilibrium with HPO4 2 minus plus H3O. That one involves both of the parts of our buffer. So that's the one that we're going to work with. We're going to use that one. We're going to use the pKa2 of 7.21 associated with that one. The third step of the phosphoric acid dissociation is not one we're using. That's the one HPO4 2 minus plus H2O in equilibrium with PO4 3 minus plus H3O plus. So we have to know when we're given a problem that involves a polyprotic acid, we have to know which dissociation reaction to use, and therefore which Ka value to use, or in our case pKa value. Okay, so the first problem is to calculate the pH of this initial solution. Alrighty, so we have identified the reaction that's occurring, and since we have amounts of both the acid and its conjugate base, we can simply use the Henderson-Hasselbalch equation. So we have pH equals pKa plus the log of A minus over HA. pH equals 7.21 plus the log of 0.80 divided by 0.80, and we get the pH to be 7.21. Notice that we have 0.80 divided by 0.80, so we have the log of 1, and the log of 1 is always 0, which is why the pH in this case comes out to be pKa. All right, so that's the buffer of our initial solution. And then part B of this problem has us calculate the pH after the addition of 0.03 moles of NaOH to 1.0 liters of this initial solution. So imagine we have a big quantity of the buffer and we take a liter of it and we add NaOH to it. Well, the NaOH is the source of OH minus. OH minus is a base, so it's going to react with the acid part of our buffer. So our stoichiometry calculation reaction is H2PO4 minus plus OH minus yielding HPO4 2 minus plus H2O. So we put those initial amounts, 0.80, 0.03 for the OH minus, and 0.80 for the base. It's a reaction that goes all the way, so we just look at the numbers. The smaller of the two is the change, so we have 0.03 as the change, negative, positive, and the final amounts for the H2PO4 minus are 0.77, and for the HPO4 2 minus 0.83. Now we go to the equilibrium calculation, and we write out the equilibrium reaction, H2PO4 minus plus H2O in equilibrium with HPO4 2 minus plus H3O plus. We put in those amounts from our stoichiometry calculation, 0.77, 0.83. Now we're ready to use the Henderson-Hasselbalch equation. So we have pH equals 7.21 plus the log of 0.83 over 0.77, and we find the pH is 7.24. So it's gone up a little bit from what it was before. Before it was 7.21. It's gone up a little bit, and that's because what we have added is base. The change is in the pH is 7.24 minus 7.21, or 0.03, and it's a small change. Part C of this problem I'm going to have you come back to and do on your own. If 0.03 moles of NaOH were added to 1 liter of water, what would the change in pH be? It will be much greater. Okay, so a review of this problem again is we have the buffer involving H2PO4 minus and HPO4 2 minus. And our initial amounts of the acid part and the base part of our buffer are 0.80 molar. They're equal. When a little bit of base is added to that buffer, the change in pH is 0.03, which is a small quantity. With that information, we're going to talk about buffering capacity. So a summary of those results are 0.80 molar H2PO4 minus and 0.80 molar HPO4 2 minus. That's our initial buffer. The initial pH we found to be 7.21. When 0.03 molar NaOH were added to it, the final pH is 7.24. The change in pH only 0.03. So that's a summary of the calculation we did above. If we had a new buffer, same buffering system, H2PO4 minus and HPO4 2 minus, same buffering system but different concentrations. The H2PO4 minus concentration is made 10 times smaller. So what we now have is a buffer that is 0.080 molar H2PO4 minus and 0.80 molar HPO4 2 minus. So come back and do this part on your own. Determine the initial pH of it. You should find a value of 8.21 and add 0.03 molar NaOH to it, and you should find a final pH of 8.43. There, the pH changes by 8.43 minus 8.21, or 0.22. The pH change now is almost 10 times greater than it was above, where it was only 0.03. So, in comparing those two buffers, the top paragraph buffer and the second paragraph buffer, we'll call the top paragraph buffer buffer 1, the second paragraph buffer buffer 2. What we have is equal concentrations in the top one and a very small delta pH, 0.03. In buffer 2, we have the ratio between the concentrations of the acid and the base part 10, or 1 to 10, and we have a much larger delta pH. Looking at our Henderson-Hasselbalch equation, which is pH equals pKa plus the log of A minus over HA, if A minus equals HA, that's our buffer number 1 situation. Then the pH equals pKa, and here the change in pH is small. That's very good because that means that that buffer can withstand added acid or added base well. If A minus equals 10 times HA, that's buffer number 2, then looking at Henderson-Hasselbalch equation, you would see that pH equals pKa plus 1 because we have the log of 10, which is 1. Here the change in pH is bigger. We found it to be 0.22. That's not as good, but it turns out within the buffering capacity area, a delta pH of 0.22 is okay. So these results can be summarized as a buffer works best when the pH at which it needs to buffer is within its pKa plus or minus 1. Thus, when preparing a buffer with a given pH, we choose a weak acid with a pKa that is within 1 unit of the desired pH. And we adjust the amount of A minus to HA to achieve the exact buffering pH. So when we have some device that we need to keep at a certain pH, we need to store in a solution, a buffer solution of a certain pH, what we do is we find a weak acid whose pKa value is very close to what we want the buffer pH to be. And then we set the A minus to HA concentration ratio to achieve the exact pH of our buffer. So I'm showing here in the table 3 buffers. In the first buffer, the pKa is 4.74. So that would be a decent buffer in the range of 3.74 to 5.74. The second one 6.37 pKa, so it can buffer in the range 5.37 to 7.37. And then we have the third buffer having a pKa in the basic range, because sometimes we need a basic sort of buffer, 10.25, so it buffers in the range we see 9.25 to 11.25. So our next problem is to calculate the ratio of A minus to HA, and specifically we're working with HCO3 minus 2 and H2CO3 needed to achieve buffering at pH equals to 7.10. Okay, so that buffer, as that's the second buffer in our table, we see that its pKa is 6.37. So 7.10, that is still within the range that the buffer should be okay. So what we need to do is determine what is the ratio of the A minus to the HA to achieve that 7.10. Alrighty, so we see what our equilibrium reaction is, H2CO3 plus H2O in equilibrium with HCO3 minus plus H3O plus. Our Henderson-Hasselbalch equation is pH equals pKa plus the log of A minus over HA. We're after the ratio A minus over HA, so we're going to isolate that. So through a little bit of algebra, we get A minus over HA equals 10 to the pH minus pKa. So we have A minus over HA equals 10 to the 7.10 minus 6.37, and we get A minus over HA to be 5.4. So that's what we would have to set our concentration ratio to. A minus is 5.4 times the concentration of HA. The solution will buffer at a pH close to 7.10 when prepared by mixing 5.4 moles of HCO3 minus and 1.0 moles of H2CO3. That'd be one way to do it, into water, or when mixing 540 mLs of 1.0 molar HCO3 minus with 100 mLs of 1.0 molar H2CO3. Alrighty, our next section is titrations. Usually we do a titration so that we can determine the concentration of a solution, often an acid or a base. And in the calculation below, rather than determining the concentration of an acid or a base, we'll calculate the pH after the addition of known concentration of NaOH to a known concentration of HCl, so that we can see what the graph of pH versus volume looks like. So pH versus volume, pH is on the y-axis, volume is on the x-axis. That is often referred to as a pH curve. So we're going to do a titration, but not as we might have done in a chem lab. This is a little bit different because we know the concentrations of the acid and the base. We're just calculating after addition of base, we're just calculating what the pH is so that we can generate pH data, volume data, and make a graph of it. And this is a strong acid, strong base titration because we have HCl, strong acid, NaOH, strong base. So our problem is 0.10 molar NaOH is gradually added to 30.0 mLs of 0.10 molar HCl. So we have let's go down and look at our apparatus. We have NaOH in a burette, and we have HCl in the flask below. Yeah, I drew those by hand. I'm sorry, they don't look so pretty, but hopefully you can picture the apparatus. So we're going to calculate the pH of the solution in the flask resulting from each of the following additions of NaOH. We're going to report the pH to 2 decimals, and we will summarize the results in a table and then draw the pH curve, which is pH versus the volume of added NaOH. Okay, so our various steps are shown as 0 mLs, 5.0 mLs, and so forth. So that refers to how much added NaOH we have added. So initially we're told to calculate the pH when no NaOH has been added, 0 volume. So we have in our flask here, our HCl flask, we have HCl. It's a strong acid, so we can just know that the H3O plus ion concentration is whatever is the concentration of the HCl. It is 0.100 molar, so we take the negative log of that, and we find the pH is, to start with, 1.00. Alrighty, next we're calculating the pH after the addition of 5.0 mLs of NaOH. Now, before we can do our calculation, we have to realize that we have added NaOH, we've added liquid NaOH to liquid HCl. So we can picture it as right before those two, the NaOH and the HCl, have reacted, we have diluted each one by the other. So first off, we have to use the dilution equation M1V1 equals M2V2 to determine the initial concentration of the NaOH and the HCl right before they react. Alrighty, so for the HCl, we have its original concentration, 0.100 molar, times the volume of it that we have initially in the flask, 30.0 mLs, divided by the final volume, 30 mLs plus 5 mLs, or 35.0 mLs. So the HCl initial concentration is 0.0857 molar. The initial NaOH concentration, the final NaOH concentration is its initial concentration, 0.10 molar, times the volume of it that we add, 5.0 mLs, divided by the final volume, 35.0 mLs. So its initial concentration that we're using in this calculation is 0.0143 molar. Let's call the 0.10 molar concentrations, those that were given up here in our problem, let's call those the stock concentrations. And let's call the concentrations that are there right after we've added the NaOH, but right before the reaction has occurred, let's call those initial concentrations. Alrighty, so the reaction between the HCl and the NaOH is shown there. HCl plus NaOH yielding water plus NaCl. Everything's on a 1-to-1 mole ratio. We do our ice table, putting in the initial amounts, 0.0857, 0.0143. Now, it's a reaction that goes all the way. It's not a equilibrium one, so we have no x's. We have the change to be whichever of those two numbers is the smaller, 0.0143. And so we do the subtraction. We get NaOH, the amount of it is 0, but the amount of HCl is 0.0714. So we take the negative log of that and we calculate that the pH is now 1.15. So it's gone up a little bit from part A by the addition of basic NaOH. The next addition of NaOH is 20 ml. So that's a total of 20 mLs that are added to the stock HCl and the NaOH. So once again, we figure out what is the the initial concentrations. So we take our 0.100 molar times 30.0 mLs. Now we're dividing by 30 plus 20 or 50.0 mLs. So we have 0.0600 molar HCl to start with. That goes in the initial line of our ice table. For the NaOH, we have it's 0.100 molar times 20.0 mLs divided by 50 mLs, we get 0.0400 molar. That goes into our table as well. The smaller of the two numbers is 0.040, so that's the change. So we have no NaOH and we have 0.020 molar HCl. We take the negative log of that, we get 1.70. So in comparison to our pH from part B, 1.15, we see the pH has gone up a little bit more. No surprise because we're adding base. The part D now is we've added a total of 29.0 mLs. So we again calculate those initial concentrations. We get 0.051 molar for the HCl, 0.049 molar for the NaOH. Those go in our ice table. The smaller of the two, 0.049, is the change. Now we have 0.0020 molar HCl left over. We take the negative log of that, we get 2.70. So it was 1.70 last calculation, now it's 2.70. Our next addition is 30.0 mLs total. So we find our initial concentrations for both of them, they are 0.0500 molar. So what we have is the point where we have equal amounts of HCl and NaOH. We're at what we call the equivalence point. If we had phenolphthalein in our flask, it would look ever so faintly pink. We're at the equivalence point, the end point. So we put those initial amounts in our ice table. We have looks like 0 HCl and 0 NaOH. Now, realize that we basically have water. We have water with salt, water with NaCl. The NaCl won't affect the pH any, so its pH is going to be 7. But how are we going to get that? Taking the log of 0, which of course we cannot do. Well, realize that in pure water, well, with NaCl, the amount of H3O plus there is 1.00 times 10 to the minus 7 molar. We take the negative log of that and we get 7.00. Alrighty, so that's the equivalence point. Now, our next problem is and the pH is 7. Our next problem is to determine the pH after the addition of 31.0 mLs of NaOH. So that means we've gone a little bit beyond 1 ml beyond the equivalence point. Our solution, if phenolphthalein were there, would be that definite fuchsia pink color. So just as before, we figure out the initial concentrations, put them in our ice table. Now we see that we have the HCl as the one that is the limiting reactant, so it's the smaller number. It's represents the change, negative 0.049. We have a little NaOH left over. Now we're going to calculate the pOH and get the value 2.70. And from pH equals 14 minus pOH, we find the pH is 11.30. So notice that it drastically went up. Just as, let's go back to a little bit before the equivalence point. So 1 ml before the equivalence point, that was part D, the pH was 2.70. And then 1 ml later, at the equivalence point, the pH shot up to 7. And 1 ml after that equivalence point, the pH shot up even more to now 11.30. The next problem, we have a total of 40.0 mLs of NaOH added. So running through the calculation just as we did before, so make sure that you can do all this, but come back and do it on your own. We get the pH to be 12.15. It kind of levels off. So here's a summary of our results, points A through G, and the volume of NaOH that we added at each step, and the resulting pH. So next, we would graph that data. And here's the graph that I got from that data. So it shows that as we start with a low pH, because of course we're starting with our HCl, it's going to have a low pH, and then we're adding gradually the NaOH, so the pH is very gradually going up. When we get very close to the equivalence point, which is 30 mLs, it starts to go up, and then right at 30 it jumps up to 7, and then just a little bit beyond that it jumps up quite a bit more, and then it levels off again. That's a typical pH curve. Here's the pH curve that's from your textbook for a strong acid, strong base titration. So we see it gradually goes up, shoots up right at the equivalence point to 7, and then gradually just continues to go up if we were to continue adding NaOH. Now picture the other situation where what we have is NaOH in our flask at the bottom, and we've got HCl in the burette. So we're adding the HCl to the NaOH. And we're measuring the pH in the flask. So it starts with a large number. We have a base, NaOH there, and we gradually add the HCl. The pH slowly decreases. At the equivalence point, it very quickly drops down to 7, and then as we add more HCl, it continues to go down, though more slowly after the equivalence point. So that's the typical pH curves, the looks of these two. We have a very rapid change right at the equivalence point, and that's what makes the titration useful for us, because we can add very little of the one in the burette and get yet a big change in pH or color change if we're using an indicator to monitor the reaction. So what we have is the equivalence point for a strong acid, strong base titration occurs at a pH of 7. This is due to the conjugates of the strong acid, strong base being neither bases nor acids. In our case, we had Na+, we had Cl- as the conjugates of HCl and NaOH. And those are just spectator ions. They don't interact with water. They don't go back to produce any HCl or any NaOH. They don't react with water. This is not the case in the titration of a weak acid with a strong base, since the conjugate base of the weak acid is a weak base. The conjugate base reacts with water to produce some HA and OH minus. What that does is to affect the pH at the equivalence point. Since we have OH minus, it makes the pH at the equivalence point greater than 7. So, for example, HA plus NaOH. So HA is a weak acid. We're reacting it with the strong base NaOH. We get H2O plus NaA. But A minus is indeed only a weak base, but it's a stronger weak base than water is. So what it does is it pulls an H plus from water, not to much extent, but to a small extent, to enough of an extent that we would measure the pH to be a little bit greater than 7. So that's what happens when we take a weak acid with a strong base. Okay, and the pH would be less than 7 in this situation where we had a weak base B combined with a strong acid like HCl, since the conjugate acid of the weak base is a weak acid. The conjugate acid reacts with water to produce some B and H3O plus, and that would make the pH at the equivalence point a little less than 7. So the example reactions here would be the titration being our weak base B plus HCl forming H2O plus HB plus. And at the equivalence point, we have that HB plus formed, like imagine NH4 plus. It's a weak acid, but it's a stronger acid than water is. So acting as an acid, it loses to some small extent H plus, forming H3O plus, making the pH a little bit less than 7 at the equivalence point. So now we will look at this problem, which is a weak acid, HA, and a strong base, NaOH titration. These calculations usually involve 2 steps. A stoichiometric calculation, that would be one where the reaction goes all the way, and an equilibrium calculation. Alrighty, so our problem is 0.100 molar NaOH is gradually added to 25.0 mLs of 0.100 molar HC2H3O2, so that's acetic acid. Calculate the pH to 2 decimals of the solution resulting from each of the following additions of NaOH. So just like before, we have the NaOH in the burette. We're slowly adding that. We have the acetic acid in the flask. And we have equal concentrations, equal stock concentrations for our base and acid. That means that the equivalence point is going to occur when the volumes are equal, and that will occur this time at 25.0 mLs. That's when, if we were doing the titration with a phenolphthalein, the indicator, we would see a slight pink color. Okay, the Ka of acetic acid is 1.8 times 10 to the minus 5. pKa is 4.74. So we'll summarize the results in the table and draw the pH curve. All right, so our first calculation, A, is at 0 mLs of added NaOH. So we simply have the acid in our flask. Now, we can't just take the negative log of its stock concentration as we could with the strong acid because, well, it's a weak acid. So we have to run through the ICE table. Notice that we have no initial amount of C2H3O2 minus, no initial amount for the A minus. We cannot therefore use the Henderson-Hasselbalch equation. We don't have a buffer. So we have to run through the calculation kind of the old-fashioned way, and we find that the H3O plus concentration is 0.00134 molar. We take the negative log of that and we get the pH of our initial solution in the flask to be 2.87. Next, we do the calculation at the addition of 12.5 mLs of the added NaOH. Alrighty, so we have diluted each one, so we have to figure out the initial concentrations. For the HC2H3O2, we get 0.0667 molar. For the NaOH, we get 0.0333 molar. So we put those into our stoichiometry table calculation where the reaction is HC2H3O2 plus NaOH yielding, so it goes all the way, water plus NaC2H3O2. So we have those initial amounts. Now the reaction goes all the way, so we have no X. We just look to the numbers. The smaller of the two, 0.0333, represents the change. And so it's negative on the reactant side, positive on the product side. We this time keep track of NaC2H3O2 because that's going to affect the pH. That isn't Cl minus, which is just a spectator ion. It affects the pH. So now we have HA and we have A minus. We have amounts of both. So we can use the Henderson-Hasselbalch equation because essentially we have a buffer. So for the Henderson-Hasselbalch equation, we simply put our initial line of the ice table there, 0.0333 molar for both HA and A minus. And then we use the Henderson-Hasselbalch equation, putting in the pKa to be 4.74 and the A minus and the HA to both be 0.0333. Notice we have the log of 1, which is 0, so we have the pH is 4.74. This is called the halfway point, the point at which we're halfway to the end point is the halfway point, and in a weak acid strong base titration, the pH at that point equals pKa. Okay, our next problem is to calculate the pH at the addition of 25.0 mLs. Now, if you recall, we had initially 25 mLs of the weak acid in the flask, and the concentrations of the NaOH and the weak acid are equal, 0.100. So when we've added 25 mLs of the NaOH, we will be at the point where we have equal amounts of acid and base. They're both 0.0500 molar. We're at the equivalence point. So we write out our stoichiometry reaction and ice table for it, putting in our initial amounts that change. Now we have 0.0500 molar C2H3O2 minus, basically none of the others. This is the equivalence point. Okay, now what we've got in our flask is C2H3O2 minus in there. Well, that's a weak base. It's going to interact with water in this equilibrium reaction, C2H3O2 minus plus H2O in equilibrium with OH minus plus HC2H3O2. We have to get the reaction correct. That's probably the toughest part of these equilibrium reactions, is what is the reaction? Well, we have to think about what's in our flask, what it interacts with. What's in our flask? C2H3O2 minus, or we could call that A minus. It's going to interact with water. it being the base, it's going to take an H plus from water to a small extent, leaving behind OH minus and forming HC2H3O2. So we put in our initial amounts in our ice table, our change, our equilibrium amounts. We also have a Kb kind of reaction because we're producing OH minus. So what we have to determine is the value of Kb. So we have Ka, we were given that in the problem. The expression is Ka times Kb equals Kw. Kb equals Kw over Ka. So we have Kb equals 1.00 times 10 to the minus 14 over 1.8 times 10 to the minus 5. Kb equals 5.6 times 10 to the minus 10. So now going back to our equilibrium calculation, we have Kb equals, from our equilibrium reaction, OH minus times HA divided by A minus, and we have 5.6 times 10 to the minus 10 equals x squared over 0.0500. We get x to be 5.3 times 10 to the minus 6. X is OH minus, so we have OH minus concentration equals 5.3 times 10 to the minus 6 molar. We take the negative log of that to get the POH is 5.27. We subtract that from 14.00. We get that the pH is 8.72. So what that represents is the pH at the equivalence point. It is greater than 7. So definitely come back and work through these problems at your leisure. Our next addition is a total amount of 37.5 mLs. So we find that once the dilutions have made right before the reaction occurs, we find the initial amount of the acetic acid is 0.0400 molar. Of the NaOH, it is 0.0600 molar. So we do our stoichiometry calculation. So HC2H3O2 plus NaOH yielding water plus NaC2H3O2. We put in our initial amounts. That's a reaction that goes all the way. So the smaller of the two, 0.0400, represents the change. So we have 0.0200 molar NaOH in the end, and 0.0400 molar C2H3O2. Now, both OH minus and C2H3O2 minus are bases. OH minus is radically stronger a base than C2H3O2 minus. So we would actually be okay to calculate the pH based only on the OH minus. If we added a little itsy bitsy contribution from the C2H3O2 minus, we would find it to be completely negligible, insignificant. So we can ignore the very tiny contribution that the C2H3O2 minus makes to the pH. So we find the POH by taking the negative log of 0.0200. We get 1.70. We subtract that from 14.00, and we get that the pH is 12.30. And here is a summary of those results. So we have the points A through D, the volumes of the NaOH that are added, and we have the pHs. We also note that the one is called the halfway point. So go to the one that's called the equivalence point. So that occurred at 25.0 mLs. Therefore, the halfway point is 25 divided by 2, or 12.5 mLs. At the halfway point, the pH equals the pKa. Okay, so next we would make that pH curve. Now, given that for this calculation we only have 4 data points, each point is so involved that I just didn't generate more. But if we had generated more, what we would get is a pH curve that looks like the blue line. So it actually goes up a little bit kind of quickly in the beginning, leveling off but always increasing a bit, and then at the equivalence point, which is where those two overlap, we have it go up, and then it just continues actually to look like the strong acid, strong base titration curve. But definitely a weak acid pH curve looks different than a strong acid pH curve. If we had done the reaction where in the burette we had the strong acid, like imagine the HCl is our strong acid in the burette, and we had in the flask a weak base like NH3, and so I'm showing at the bottom what that reaction would be. Our pH curve would look like the one here at the bottom. It starts at large numbers because in our flask we have the base ammonia, NH3. So it gradually drops down as we add the HCl, making a bit of a stronger drop at around the equivalence point, and then it continues smoothly to decrease. For this titration, depending on what the exact concentrations and all are, but its pH at the equivalence point is around 5.3. So next we have another kind of calculation that we might make with a titration type problem. So we have, like our very first example of titrations, we have NaOH in a burette, and we have in the flask HCl, and we have phenolphthalein in our flask. And so let's say that this titration is one that we do in order to determine the concentration of the HCl in the flask. So we slowly add the NaOH until we get just the slightest pink color. So here's our problem. What is the concentration of HCl? So that would be the original concentration of the HCl in the flask. If it takes 37.50 mLs of 0.100 molar NaOH to neutralize 25.00 mLs of HCl. So in our flask initially we have 25.00 mLs of HCl, and we're adding the 37.50 mLs of 0.100 molar NaOH to it to get to the equivalence point. So our reaction is HCl plus NaOH yielding H2O plus NaCl. So we know a lot about the NaOH. So what we're going to do is determine the moles of NaOH that we have, and then we will do the 1-to-1 mole ratio between the HCl and the NaOH. Alrighty, so we take those 37.50 mLs and we convert to liters. We get 0.03750 liters. Then we multiply by the molarity, 0.100 moles NaOH per liter. That now, notice liters have canceled, that gives us moles of NaOH. Now we use the 1-to-1 mole ratio to jump to moles of HCl. That's moles of HCl, 0.00375 moles. And we will divide by the volume, the 25 mLs converted to liters, to determine the molarity of the HCl. So we're dividing by 0.02500 liters, and we get that the molarity of the original HCl would be 0.150 molar. So what we would do is we would have a big container of HCl that we have made. we want to know what its molarity is. So we would take a quantity of it, in this case 25.00 mLs, and we would titrate it. And therefore we would know the concentration of our big quantity of HCl. So next and last, we have a kind of cute song. At least I thought it was cute when I saw it, and sorry it's kind of tipped to the side. It's Good Titrations, Ode to a Lab Partner, and it's sung to the tune of Good Vibrations by the Beach Boys. So run through it as you have time. So that is it on chapter 15. Definitely lots of stuff we talked about, lots of reactions you need to think about. And so go back through the video, lecture video, as it helps you slowly go through it. Definitely go through the handout, go through each problem on your own, covering the solution, make sure that you could do them. The toughest part, I think, in these equilibrium calculations is often coming up with what is the right reaction. So you have to think about what's present. What is it in? How does it interact usually with water? Read through chapter 15 in your textbook, do the assigned homework problems.